Hello guys, thanks for coming. This paper reading session, we're gonna take a look at a paper called Efficient Training of a Neural Transducer for Speech Recognition. It is R&D training, but the interesting thing of this paper is that it uses just one single GPU and train a model which only takes 2 to 3 weeks, and the performance on libre speech was as good as the super large transformers, which use the lots of GPUs to train for weeks. Okay. Also, I want to show you my new T-shirt. Fortunately, if I talk closely to my mic, you won't be able to see it. Okay, let's start. First of all, the author gives us a short introduction of the model he's working on, the R&T, the recursive neural network transducer model, and because it's not only it's good in performance, but also the most important thing I think to me is that it's streaming in nature compared to the AED model, or some people call that transformer, right? And so here, these guys propose 3-stage progressive training pipeline. Instead of just using one training stage. Okay, let's see what they do. They of course they talk about the basics of the R&T. I guess this is known to all of us, but I will give you a short overview of this. So the purpose is to maximize the posterior of this, right? And the A1 to S means the decoded sequence, okay, or the sequence, label sequence. But of course, the label sequence, the length of that is S, is significantly shorter than T most of the time. For example, we have a 10 seconds of audio, and that means we have 1,000 frames. The T equals to 1,000. But the letters in this sentence might just be 100. Okay. And what does the flower B mean? Okay. I think the flower B means sometimes it's hard to manage them. Okay, then you can see the author said, okay, so this probability is equivalent of this probability sum over all the possible passes. Okay, where do you get the pass? Okay, this is how you get it. And the B means that to remove, the B operation means to remove all the blanks in the label sequence, and the reverse inverse or reverse function of B means that to augment the label sequence with the blanks. So this one's length is equivalent to T. Okay, these two, their lengths are equivalent, and you can see that because you have lots of what do you call that, encoder outputs. Okay, this is how you get different paths from going from the H to Y. Okay, and then you have to sum over all of this, then you get this probability. And of course, if you assume that, okay, the current output of the YT is only dependent on the output of the Y of the previous time plus the current encoder's output, then you can write this function into this by applying the independent assumption. Okay, This is fairly easy to understand. Okay. Standard thing. And then the question becomes, how do I solve this? Or this one, you can see in this equation, it can be written as this. So of course, the b y of t to 1 to t minus 1, so the history, okay, the history after it being augmented, it can also be so you can do augment, right? But if you look at the labels before the augmentation, so that can be used as sufficient statistics here. So this one can be just reduced to the label sequence, okay? And then furtherwise, you can say, okay, I don't think the current label is dependent on the whole history of labels. It only depends on the K labels before the current time. So it can be further reduced. You can see the operation is all about reducing the complexity, okay? And then the next thing they want to do is, I think this is known to us. If you want to do decoding, definitely you're doing the, like the author mentioned, you're doing the maximum posteriori decoding, right? Of course, you can just look at this. But suppose you want to add a language model. And so this is the term you want to add, okay? But the thing is, because this is assume that your R&D model, the model is a composure of the acoustic part plus the language part. So you think about the hybrid model, HML model we talk about, right? So we train the acoustic model, language model separately. The reason we call the R&D model or AED model a end-to-end model is because that the model is a composure of the acoustic and linguistic or language, okay? So this term is to remove the language model factor from the trained R&D model. And this language model is an additional term to represent a bigger language model or the domain-specific language model. So you see what I'm saying? So people have found out this can improve the decoding accuracy or reduce the WR. And the author called that ILM, internal language model technique or something, okay? Then we can move on to what the author proposed, okay? Definitely, if you want to train a R&D model, you gotta have to maximize this, right? No, minimize the loss. Okay, they have the minus sign there. Minimize the loss, but they call that, the author called it this to be a FullSum loss. FS means full sum. Okay, in this paper. And after this, usually you can apply the minimum Bayesian risk sequence discriminative training or discriminative training. Okay, SMBR. Usually, if you see SMBR sequence discriminative training, I think this is one sequence discriminative training method, but you do have, I think MMI is also sequence training, right? But the SMBR is fairly commonly used in the R&D training. Why? Because think about the SMBR training. You gotta have to define a risk function, which is shown here. It's called RA versus the RA, the decoded A versus the reference A, or hypothesis. Sorry, hypothesis versus the reference. Okay, and usually you say for the R&D training, it's very easy to do this because the output of the neural network is a label sequence, right? You can just compare calculate the Lagrange distance or the WER, okay, by comparing the hypothesis and the reference. But in the HMM or the Coursera model training, calculating the risk function is sophisticated because you do not have the sequence at the output of the acoustic model. You only have some state output, right? Yeah. And then you can see that this is a risk function, and this is the nominator term, and this is a denominator term. The denominator term, you can just regard them as the competing hypothesis versus the reference. Okay, so you want to, because you want to minimize this loss, right? I think the R is have a negative sign here, right? So you want to maximize this, right? So in order to, this is something minus. It's a negative. It's a negative. This is why you want to maximize the probability of this, the denominator, and then minimized the denominator term. So you want the probability of the reference to be as high as possible, and the other competing hypotheses to be, their probabilities should be as low as possible. Okay, this is the idea of discriminative training, and the R part defines the risk. Okay, the risk function. This is standard. Okay, if you're interested, you can go and check the papers. Here's what they do. Okay, first of all, they talk about the vertebrate training. For those of you who are not very familiar with this has been commonly used in the hybrid model training or the acoustic model training. Why? Because in the acoustic model training, people are not training the word model or word piece model. They're training something called a state model. So this is why for the HMM training or the acoustic model training, you have to have a preparation stage, or which is to say, okay, you have the labels of the word level label and the audio. How do you align each part of the audio to a specific phoneme or the state of the phoneme? Okay, and indeed, I think if you look at the common or the Euro acoustic model training, people are doing actually vertebrate training. Okay, because you know exactly which part of the audio it corresponds to the specific state. Okay, so you have an alignment stage before the training to get the alignments of the audio from the audio to the states. But this is the same thing. Although I think they're using either phoneme or word pieces, but the idea is the same. First of all, they train a CTC model. You can see the equation, okay? No, this is not CTC loss, okay? First of all, they train a very vanilla CTC model, small CTC model. For those of you who do not know CTC model, you can check lots of tutorials online. I'm not going to do it today. And the CTC model gives you the alignment. Okay, for instance, given this part of audio, it corresponds to this label. Remember, the label has been augmented, so each frame has a label. Okay. And the vertebrate training thing, you can see compared to this equation, your vertebrate training is this equation can be written as this one. So they have this type of independent assumption. So this thing can be break up in at the different time t steps. Okay. And this is very fast because each frame corresponds just to one label. Each frame corresponds just one label. This can be trained very fast. Other than, you take the whole utterance as input, okay, then you get the label sequence. So this is complexity wise, it's significantly reduced. Okay. And also they applied a encoder auxiliary loss. What does this mean? I think this is a vanilla CE loss, and you see there's no attention. This thing can be done very fast, no attention, and it's also frame wise. You see, it's also frame wise. The difference from this one to the vertebrae is that the vertebrae training, the encoder output is from 1 to t, but this one, the encoder's output is only just at the time ht. Okay, and there's no history. And third thing is the boosting. The boosting means that they want to emphasize on the occasion that when the non-blank label is presented, okay, just to see that the equation is the same as the L vertebrae, but they have this extra term. But just to boost the importance of the certain output labels. That makes sense. You don't care too much about the blank frames. Okay, then it's a summation of the 3 terms with weighting factor. And this can be trained very fast. I hope you can understand this. But after doing this, then they say, after this, they get to a good local optimum, but they do want to reach some global optimum, or at least try, okay? Then they try the FullSum fine tuning. Oh, this is standard, okay? But the thing is, other than going directly from randomly initialized matrix to the using the FullSum fine tuning, it takes a longer time to reach the optimum point. But by using their method, they can first go to a good local optimum. Then they show that from that good local optimum, it's not that difficult to go some extra few epochs to reach the global optimum. So this one is, in overall sense, saves the training time and the number of GPU cards. The other thing is that the stage 3, they mentioned that the fastest sequence training for LM integration. I think this has 2 factors. You can see that. First of all, the first 2 stages doesn't have the sequence training or SMBR. And the third one, the next factor here is the LM integration. Okay. I think if you see the equation, how the language model was integrated, it's very simple. I think it's not new. So here is what they do. They applied language model to the first pass decoding result, such that they can generate the embedded list. I think they did something like on the lattice, and they generate embedded list from the lattice, so they call that a faster sequence training. But I don't see that. Maybe they say, okay, what they're trying to say is that, okay, because I have a lattice, it saves time to generate the embedded list. I think that's what they mean, but it's okay. I don't think that they should use the name of fast here. It's not fast, I think. Yeah. So eventually they're saying that the finalized SMBR loss is the SMBR loss plus a regularization term, which is the FullSum loss. Okay. Okay. Yeah, static embedded generation. Okay. That's what they're talking about. They use a lattice. Yeah, there's some details. If you're interested, you can read it. But I don't think that's much new here. The learning rate scheduling, I think three-phase scheduling. The first is from 0 to 45% of the total steps. They linearly increase the learning rate. Okay. And then they linearly afterward go to 90%. They linearly decrease LR peak. Oh, this is the peak, okay? It's the same speed to decrease, right? And then linearly decrease. It's also linear, right? Okay. Linear one. I think it's different than what I'm seeing usually. I think usually it's like a warm up, then hold, then decrease. I think something like this. Or this, something like this. Right? Yeah, usually what I saw is has a holding stage. But anyways, this is their linear rate schedule. Okay, experiment. I think they did have done lots of experiments. This is what I like, why I like this paper, because it allows the people to see the difference between each configuration and save people who read their papers time. Right? Okay, sometimes you don't have to do some experiment because they have done it. They've done it for you. That's the good thing of reading paper. Okay. First of all, let's see the training stage 1 and 2. Remember, the training stage is one is the vertebrae training. Okay. The second stage is a full sum tuning. Okay. And the LBS means Libre speech. SWB means switchboard. So let's look at this one first. Yeah, I think they also, this is the unit here is the phoneme. Okay. And this idiom here, I think it's ADSM. I think it means word piece. This is a phone. If you look at the results wise, their phoneme base is always better than the word piece. So I think I would just for the rest of the explanation, I would just focus on the phoneme results. It's interesting that they didn't compare on the test clean and test other for at this stage. This is the dev clean, develop clean, dev other, which means that I haven't seen their code, but recently people just use the dev clean or dev other together as a dev set. So how do you say that? The model is overfitted to these two sets, okay? And then you can see that in the first stage, they only trained 20 epochs. For the CTC, they got, but Dev Clean already got 2.9. It's very, very good. And this was achieved under the foreground language model, which is a very weak language model. And then they apply the FullSum training, then they were able to reduce this to 2.6, which I would say it's not that good, but it's already good, very good. And then if they use the transformer language model, you can get 1.8. 1.8 is a very good number compared on the dev set. Okay. Then they also look into the details of the vertebrate training, and they say that suppose I use various of different CTC model for doing these alignments, and then I get different alignments, right? And they say, okay, this is the alignment CTC model. You can see if you're using this CTC model, what the error rate you're gonna get. Okay, actually the error rate is very high compared to this ones, right? You can see the error rate mostly is about 7%. Sometimes it's almost 10%. And then they use the they use the conformer in CTC model already. And this one might be a big model. I think also this is interesting to me, or smart. And so suppose you can get a very, very good CTC model. I won't call CTC model better than the transformer model, but suppose you take your time and train using lots of cards and lots of days to train a fairly large, good CTC model. You can use the CTC model to do the alignments on different sets, data sets, right? And then you can get good alignments. And you can see here, suppose I use the BLSM model, and then I for the stage 1 phoneme transducer, then you can see that I can roughly get 7.7 word rate. So it's improvement over the CTC already. And then they say that if you're using this better CTC model, which has a lower WER, then you can get 6.9 accuracy. I think this should be merged. Okay, I think this archive paper. So that the conclusion is that you should use a good CTC model to run the alignment for the first stage vertebrate training. And then let's take a look at table 3. What does the table 3 do? So it's interesting that they only use one single GTX 1080 Ti GPU. I think this is almost a 6 years old GPU, okay, before when it was released. Of course, it's slow, right? Each epoch will take 18 hours, and this one will take 700 hours. I think that's about 30 days. Am I right? 30 days, 1 month. And then you can get 2.6. Oh, sorry. This is the standard. So if you are just using this card to run the FullSum training, the standard R&D training, you can get 2.6 on dev set, but it's gonna take you 1 month. Well, suppose you're using their proposed method, stage 1 vertebrate training. It's called 6 hours per epoch. So this is 120 hours. That's 5 days. Am I right? So stage 1 is 5 days. And stage 2, they have 15 more epochs. I think this is like Correct me if I'm wrong. This is like 10 days. Okay. So in total, this is half month. Am I correct? And saves half amount of time compared to the full standard training. Yeah, of course. You see, this is why they say, okay, they save the full sum epoch by 25 epochs. You see, originally you need 40, but you only need 15 here. Or do they mean that in stage 1, it's almost take no time? Yeah, this is something I don't know. I think stage 1 still takes time. You can see that. Okay, let's take a look at table 4. This is about the WERs and the language model integration effort of stage 3 training. Remember, stage 3 training, it has the sequence training plus the language model integration. Okay. Results evaluated with a stage full or some full. Okay. Yeah. Again, we only look at the phoneme transducer model. Is it transducer? ADSM is not, the performance is worse than that one. So you can see that if you're using transformer language model at stage 2, you get 4.1. But if you're using the internal language model technique, then you can reduce the WER by a little bit. But the interesting thing is that at the stage 3, whatever you did, I think they play around with the what do you call that? The weighting factor or scaling factors of the language model. The WER didn't change after they integrated the language model. Okay, but for the switchboard, the performance increased a little bit. Okay, I think this is also known to most of us. The integration of the language model does not work as good as the theory looks like. Okay. FullSum. The FS means FullSum fine tuning. Yeah. They created this term. Okay. But they didn't mention how fast is this. This is, I think, they should do exploring whether this stage 3 saves some time or not. Okay. Okay, then let's take a look at table 5. So all the works here are some published work. You just use and put the numbers here. You can see on the test clean wise, the methods, I think this is RNN, right? This one is not RNN. It's a hybrid model, the acoustic model plus transformer model. Model is smaller, but the performance is the worst of all the 4 models. This one is a transformer CTC. It works very, very well. This is a conformer plus transducer. Seems like it's an end-to-end model. And you can see that most of them are around 2% accuracy, error rate in the test clean set. And I think most of them they use the word pieces. And for this paper, you can see that when using transformer, they can get 2.1. And if you're using word piece, they can get 1.9, which is as good as the other models. And you can see that their model is significantly smaller than the other 3 end-to-end models. You can see this one, every one of them is larger than 100 megabytes. And you can see it's taking 600 epochs. That's bizarre, man. And this one only takes about 40 to 30 to 40 epochs, and they can get a similar results. On test other, I think the best one you can get below 2%, but this one you can see that their phoneme based transducer, they can also get about 4%. Okay, so I would say this result is very impressive to me. And this is the results on the Libre speech. The previous result was on the Libre speech. This was on the switchboard. And you can see these are the published works. And you can see again, this one is the hybrid model, and these three are end-to-end model. Okay. You can see the end-to-end model takes more than 100 epochs to train. And you can see this one works the best. Oh, this is like a tricky part, you know. This is not standard evaluation. They use a cross utterance evaluation. This is not standard switchboard. And they get better results on the Hub 5 test set. You can see that most of them are around. I look at this most of the time. So this is about 10%. Okay. Switchboard is a spontaneous speech. Two people having a telephonic conversation. But if you look at this, by doing the transformer, they can get 9.2, which is fairly good to me. And they use less amount of epochs. You can see, compared to this and this, they have better results, right? But it's interesting. I think I need to take a look at reference 28. It seems that the model is smaller than this one, but it doesn't have more epochs to train. The language model is weaker. Yeah, I think I recommend you guys to read this one. Seems this is also impressive work. I think they do something R alignment or something like this. This is my okay. I think this is what they mainly propose. And you see the conclusion, they say that they're able to build a sort of performance model which does not have pre-trained model, doesn't have a self-supervised model, and the database size supposes only about 1,000 hours. 1,000 hours. They can train this amount of data into a R&D model with a single GPU in 2 to 3 weeks, which is fairly impressive. And thanks for watching, and see you next week.